one last little concept that's particularly important when it comes to telescopes and microscopes. We mentioned this a bit before. It's called resolution. To be able to resolve means you can look at two objects and see that there are two physical objects there. The example I used before was those paintings that are dots of color. You stand close enough to it, you can see all the individual dots. You back up a little bit and you can't see the individual dots anymore. It looks like any old normal painting. Resolution has to do with being able to see the individual dots. Okay? So for example, let's say we're looking up at the North Star. Turns out the North Star is actually a binary star system. There's two stars there. You just can't tell that there are two stars there because our eyes cannot resolve them. If you have a telescope, you certainly can see that there's two stars there.
So which one's the North Star?
Well, as far as we're concerned, they're far enough away to both be the North Star.
Is that what increases the intensity of the light?
It would be bright. It would appear brighter to us than if it had just been one star, yes. Now, the whole concept of resolution goes back to the single slit aperture, the single slit interference, but technically the circular aperture interference. We had theta was equal to 1.22 lambda over d. Please remember that theta needed to be in radians. Turns out each star in this case needs to create its own individual interference pattern on your retina. As long as their interference patterns do not overlap, you will see them as two separate stars. If their interference patterns overlap with each other, you just see them as one star. So the minimum angle, if we were to draw from our eye or from our telescope, whatever our aperture is, if we were to draw a line to one of the stars and a line to the other star, this angle has a minimum value that it can have and still be able to resolve the two stars. This is the minimum value. Lambda would be the primary wavelength of light coming from those stars. D would be the diameter of whatever you're using to look at it. If you're looking with your naked eye, this would be the diameter of your pupil. If you're looking with binoculars, this would be the diameter of the first lens the light passes through. If you're using a telescope, this is the diameter of the objective, be it lens or mirror, whichever type of telescope you happen to be using. So that represents the smallest the angle can possibly be and be able to resolve what you're looking at. We can relate that to the geometry of the problem. If we call this distance L, the distance from our telescope or binoculars or eyes, whatever it is we're looking through, out to the stars, that distance is L. The distance between the stars we'll call, I don't know, we can call it Y, for example. We can call it D, just not big D so you don't confuse it with the big D over here. A?
D. Just something we don't usually use.
You can call it whatever you don't want, please. Geometry of the problem. Tangent of theta, y over L. This angle is very, very, very small. So the tangent of theta is approximately the same thing as theta, as long as theta is in radians. So theta, in terms of the geometry of the problem, will equal y over L. Since both of these are equations for theta, we can set them equal to each other. So for example, y, the distance they would need to be apart would be 1.22 lambda L over D. So for example, there were a lot of claims at one point in time that people looking through their backyard telescopes, we're seeing the footprints of the astronauts on the moon. Okay? How big of a telescope would they actually need? The diameter of their objective. How big would the telescope actually need to be to see the footprints?
So Y would be like 1 foot.
Yeah.
This is what they do at NASA, huh? This is how they disprove people.
So yeah, let's go ahead and just say Y is about 1 meter, maybe?
It's a big foot.
Yes. Well, we're not looking at the size of the foot, we're looking at the footprints, from one footprint to the next. L. L would be from the surface of the Earth to the surface of the Moon. The distance from Earth to Moon, center to center, I just brought the astronomical data in. It's from the back, inside the back cover of your book. So the distance from the center of the Moon to the center of the Earth is 3.84 times 10 to the 8th meters. If we subtract off the radius of the Earth, which is 6.37 times 10 to the 6th, and subtract off the radius of the Moon, which is 1.74 10 to the 6th, L, the distance from this person's telescope to the Moon's surface would be 3.76 times 10 to the 8th meters. Now, the whole reason we can see the Moon is because it's reflecting light from the Sun. The primary wavelength emitted by the Sun is actually green. Kind of sounds a little odd because the Sun certainly doesn't look green. It's so stinking bright, it looks almost white. But if we had a spectrometer where we could separate light into its individual components, the primary wavelength from the Sun is approximately 550 nanometers. So that will be the primary wavelength reflecting off the Moon. So Y is not what we want. We have Y. We want D. So D will be 1.22 lambda L over Y. So 1.22 lambda 550 nanometers. We'll need to put that in meters. I'll do that when I plug it into my calculator. L 3.76 times 10 to the 8th meters. Y approximately a meter.
Nano times 10 to the -9.
Yes. Nano is 10 to the -9. Well, divide by 1. Really need to do that on my calculator. Goodness. The telescope would have to be 252 meters in diameter. That's a couple of football fields. No one on Earth can look through a telescope and see the footprints on the Moon. It's not possible. Okay.
Nice idea, though.
The Hubble.
I don't know that the Hubble can even do it, actually.
Is the Hubble, how big is it subjective? It's like,
Well, it's closer.
I'm not sure. It's not significantly closer.
I wanna
It's
say-
in orbit around the Earth. It's pretty close to the Earth.
it's probably at most like 5 meters.
Right. I don't know what it is, but yeah, it's nothing like that. Certainly.
Let's ask Google.
Love the instant information.
Let's ask you. I have something cool to tell my wife today.
So telescopes, they need to be pretty darn big in order to resolve objects.
Well, they're 1 meter apart.
Right, exactly. On Earth, I can't remember how big the biggest refracting telescope on Earth is. It's like 3 meters or something like that. Refracting telescopes are harder to make big compared to reflecting telescopes where they use a mirror for the objective. Refracting telescopes, can you imagine making a huge old lens?
It would
And
be
then
perfect. It would crush itself on
the lens itself, the weight would distorted over time because glass is fluid. But we also run into the problem that different wavelengths of light have different indices of refraction in the material. So you get what's called chromatic aberration. You get distortion in the picture because red focuses at a different focal length than blue does. So they all focus at a different wavelength, or a different point.
That's why you use a mirror.
Mirrors are great. Mirrors don't have that problem, and they're much easier to make a big mirror because you can support it everywhere. You don't have to worry about the light having to pass through it.
So the Hubble was a mirror.
A mirror.
Even I was overestimating it's 2.4.
Oh wow, so 2.4 meters for our Hubble telescope. Cool. But yeah, so we've gotten some fantastic pictures from that thing, that's for sure.
Well, they've got these new telescopes where the objective mirror is like lots of hexagonal,
Oh, yeah.
where each one is its own piece,
Right.
so that it doesn't fall apart under its own weight. So
Right.
they can just honeycomb it out and make it massive.
Exactly.
That's going to be cool.
The other thing they can do, the linear array they have in New Mexico, if you ever saw the movie Contact, they have a whole bunch of telescopes. It turns out if you focus all of those telescopes at the same source and get pictures from it, if you add all those pictures together, it's equivalent to getting a picture from a telescope as big as the area they take up.
That's cool.
And so it's called a linear array, and they add pictures together and get a nicer resolution out of it.
You could put a bunch of telescopes
Right,
with the diameter of that.
exactly. I don't know how well it works for visible light. It works much better for radio waves, the linear arrays do.
Taking pictures of radio waves.
Yeah, they're false color pictures. They just assign a color to the different wavelengths.